Hi, class. Lab 2 is about to find the formula of the inorganic compounds with associated number of waters. So here we call hydrates. So you will, according to the lab experiment, you needed to find out the formula of three inorganic compounds with their associated water molecules. So let's look at the inorganic hydrates. Hydrates are inorganic salt that contain water molecule as a part of their structure. On the next slide, I will tell you why some of the inorganic salt will have associated waters. So for this case, the salt are usually contain a definite amount of water by weight. So here we say that definitely means normally it's kind of discrete number. For example, integral 1, 2, 3, 4, 5, so on and so forth. It's not like somehow we have a half water, like a 0.5 or 0.1. This is where we see some kind of like your salt, they get a weight. So if that get weight, that means may contain different amount of water. In this case, there's no actually proportion of water versus the salt. So for those associated waters, here we talk about those hydrate water, not those because of get wet. Get wet is something easy to remove them, right? For example, if you have a salt, let's say you have a sodium chloride, and that's a weight mixed with water, right? And you leave outside to the atmospheric pressure, and those water will gradually dry, just like your clothes get wet and after a while getting dry. So those water can be easily removed. However, for those associated water, that will become a part of the compounds, and you cannot remove them just at room temperature exposed to the like sunlight, something like that. Okay, so this case, in order to remove those associated water, you can do heating. So this case, we do heating. I will tell you on next slide. I will tell you why we will do heating. We will be able to remove those associated waters. So once those associated water are removed, the resulting materials left we will call anhydrate compounds. In this case, so that we'll call anhydrate. Now, these anhydrate have different properties from those hydrate. Particularly, if you see that, like, so this one we say anhydrate are readily soluble in water, compared to those hydrate. Hydrate normally has less solubility than those anhydrate. Another thing is big change is color change. And I will show you later on why we want have the color change. So the color change can tell you to test that if water has been removed or not. And we often use this one to put in the refrigerator or something to see that one is get wet, absorb the moisture or not. Anyway, so here, so that's how if a hydra has a different color, it will revert back upon dissolution. That means if you have an hydrate, once you mix it with water, that can reform those hydrate and regain the color that one wants to change it, right? So the hydration and the dehydration process are always reversible. So this one is reversible under different conditions. For example, for the dehydration, often you require heating. So we have a heating. But for the rehydration, simply you mix with water, then that will rehydrate. So this one for the dehydration, rehydration is simply added water. So on the next slide, I will show you why different compound, different inorganic compound has different number of water associated. So let's see, we will look at the couple, right? Couple has an atomic symbol like this Cu, right? So if you look at the electron configuration, that should have, so let's see, has an argon in the inner electron. So we, after that, we will have, so this one's the inner, then we have, so look at that, we'll have 4s1, right? And so 4p and 4d, something like this. let me rewrite that from beginning. So electron configuration, we have 1s2, 2s2, 2p6, 3s2, 3p6, right? Then we will have a 3d, 10, 4s1, 4p, 4d. Now notice that here, for those here, you can see those are the fourth layer, and there's only one electrons. So for the couple to form the couple two, let's see that, requires to lose this electron. So this one electron was lost, plus here, you will lose one more electron. So that one has a configuration, will have 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, right? 4s0, 4p0, 4d0. Now, notice that those are the inner shell. We will have those, consider that. Now, you can see even this one's 9, right? And we remember for the couple, the copper cation, the copper cation, this one has a coordination number. We will say that coordination number. So here, coordination number of 6. So Y6, so you can see that one has a geometry, can form the geometry of a hexagon or octagon. So here you can see one top, one bottom, and this one is square. So you have one here, here, and the top and the bottom. So that this one sitting the, so this will form the hexagon, because if you connect them, that actually form this, right? So you can see that form the octagon. So form octagon. Now, but so they have a coordination number 6. Now, why 6? So what's the hybridization? You can see all this, there's no electrons. So they can do sp3d2. So total here 1s, 3p, and 2d. So total give you 6, right? Total 6. Now, if that's the case, say this one has a let's see here, copper 2 plus, right? And the sulfate, this make it neutral. But since this copper cation has 6 coordination positions, right? 6. So here, one here, here, and here, and one top, one bottom. And each position can be occupied by a water molecule, for example, here, water, let's do that. So this one, d orbital, well, so since we have a sp3d2, this 6th orbital hybridized to form this 6 of the sp3d2 orbital. So here you have all those are the empty. So this pair of electron will be, so think about those has the 6 different orbitals, right? Like this. So water molecule will be able to occupy this one. Likewise, you may have another water molecule here, occupy this one, and then another water molecule occupy this, and then another water molecule occupy this. Then up to here, you can have another water molecule up to this one, and then this one sulfated to occupy this one. Now, this kind of orbital, or the molecule occupies the empty orbital, we will call them coordination covalent bond. Now these bonds are stable, right? But not as stable as regular covalent bond. And from this one, you can see here actually, except this one, there are 5, right? 5 water molecules associated with this copper cation. So that's how, for those copper sulfate, we often write them as a copper sulfate and a 5 hydrate, because they can only associate with this one's discrete number, actual number here. You will not have something like a 4.9 or 4.5, something like a half number or some other numbers. Must be 5. This explains why that one is 5. And also, since those numbers, so we have 5 water here associated. Now notice this bond, I said that one is stable, so that's how they will always form 5. But on the other hand, this was not as stable as a regular covalent bond. So that's how once we heat, provided heat to that, those can be removed, the break. So that one formed the anhydrates. Now, remember, in this case, this is the orbital. Notice we have, if we have an orbital here, and so you have, so like those here, those are the empty orbital, sp3d2 orbital, right? There's no electrons. Now, once we fill with electrons, right? And then your night will excited to go higher, so they can have an excitation. So that's the reason for the cup. Once you have a hydrate, this one show blue colors. But once you remove all those waters, or there's no electrons, so there's no excitation, so that become a white color or colorless. Colorless, or you can see that colorless. And from here, this explains why the copper sulfate, we will see that copper sulfate anhydrase is white, but with 5 water associated, that will show the blue color. Because of that, a lot of things we can use that, like nickel, right? Or cobalt, like cobalt. So for example, cobalt, this one also associated with water, right? And then this one will show colors like will change to pink to blue, with water blue, without water pink. So we can use that as a form the gel and put in refrigerator, use this as an indicator for moisture. Once this blue gels absorb the water, then that will form hydrate and will show the pink. So this case will show pink colors. Okay. So, and today we will, because of that, today we will test the associated water with copper sulfate. And in this case, we have a Z or X to tell, we don't know actual number of that. Then we will do is calcium sulfate and how many water, and likewise cobalt and how many water. So that's what we will do today for those measure those numbers. But how to measure these numbers? So here you can see if we use this one as an example, copper sulfate, and suppose here we don't know the actual number of water here. Now in this case, we can measure the total weight, so the mass, right? Then for this case, we will take those samples and heat them, put in the crucible, put inside, then we use a flame to heat them for 10 minutes. Then after that, it will cool down and then we get the weight, get the mass. In this case, mass, supposedly if all the associated water are removed, then the mass should respond to the actual mass of this one, copper sulfate. So we have the mass and the mass two, like the mass one, mass two. So the difference will actually equal to the mass of water, right? Now, according to the mass, we know that the mass has the relationship. So the number of moles, for example, number of moles equal to mass over molecular weight. So this can, using them, so we plug in, for example, here, right? We will have the mass water divided by molecular weight of water, that's 18 gram per mole. This gives us the number of moles of water. That will show how many moles of here. Then look at that, this mass 2. So N prime equal to mass 2. So divided by the molecular weight of copper sulfate itself. This will give us the mass number of moles of this one, right? Moles of this one. Then according to that, we can use the moles of water we found out from this equation divided by the moles of copper sulfate. then that we found that the ratio should reflect the value of the Z here. That's a principle for our experiment today. So you can apply this. Now remember here, during the heating, we really don't know when the water or associated water are completely removed. So after heating, we measure the mass. Then we need to heat again. So this time we heat for 5 minutes and then cool down. And then we found that if there's two mass we measured are very close, so we will assume all the water are removed. Otherwise, you have to continue to do until you will see the mass are very close. Then you see that's fine. All the water has been removed. Now here, another thing is when you have put your sample in the crucible and the lid, you cover the lid. You cannot fully cover that because when the water vaporizes, removed, they will condense at the top of that. So you actually not completely remove. So you have to leave some opening, allow water to evaporate, get out of those crucible. So that's how you will completely remove the water. Anyway, let's go. So here you see some hydrate are not stable under ambient conditions of temperature and humidity. This is the case not stable. Some will compound like that. Okay. And there's some hydrate or loose water at room temperature, like some of this one. You can see sodium sulfate with 10 associated water. And in this case, because sodium, think about sodium, outside sodium is small, outside it probably is not be able to hold it up to 10 water molecules. So that's how some of water will be naturally dissociated. And there's some other sort of we call hygroscopic hydrate absorb water from their environment, like calcium chloride. This one, the anhydrate, supposedly will be powder, or it's a kind of small particle like this. But you leave it outside to the like air. Then after a while, this will absorb lots of water from the air, and this one will dissolve, become a wet, and finally become a solution. Now, another type of unique synthetic hydrates will absorb water from the atmospheres, and that you can see undergo self-dissolution. This one just like sodium chloride, and even for this one, will have some property like this one. So here for the inorganic hydrate, we will give general formula like this one. This stands for the metal, and this stands for the anion component. And here will be a different amount of water associated. And in this case, X and Y reflect their ionic state here, well, you can see the charges associated. Now, A can be a single atom, such as chloride, or fluoride, something like this, or oxygen, something like this, but can be as a kind of oxygenate. So, for example, perchloride or iodinate or something like carbonate. So, can be some of these, right? So Z is the number of abundant water molecules. So example like this one, sodium carbonate with 10 associated water, right? We call washing soda. And the magnesium sulfate and something like this. And the barium sulfate, you can see each one has different number of water. So, so the general formula does not indicate a structure. Why is that? Example, I will show you here. Back to this one again. Example, this one. The actual structure you will not see. So each one, remember, those are the inorganic hydrate. And then later on, when you start general chemistry, you will find out that those ionic molecule, actually, we can only use this one. It's a we call molecular formula. Well, we call formula. So it's basically, this simply reflects the minimal ratio of atom inside those. So, well, actually, we will call here, we will call empirical formula. Empirical formula. That reflects the minimal ratio of the atoms within these compounds. This one is completely different from the molecular formula, which we will write, for example, ethanol. This one is a molecular formula, so that will have a C2H6O. So this one means no matter where you find this molecule, well, at any state, for example, in the gas phase, or in the liquid phase, or in the solid phase, they will be always the same. So this case, no, so even you hit that, will still keep the same. So this we call molecular formula. And in this case, we will only call that as the empirical formula. And so here, you can see copper actually can associate with something like this one. Here, water, right? Water we draw earlier. And top here can be water. Can be something like this, for example. And here copper again. And I continue. And the bottom also continue. Something like this. You can see continue to do that, form the network. So those are, it's not a simple, very small molecule, actually form a very large, like a crystals. That's how you will see that. So those particles are very difficult to dissolve in water. For the hydrate, like this experiment, you have a general formula like we described earlier. So once we apply the heat, you will generate a hydrate for this one, and plus a different amount of water will be evaporate, right? So you will measure the mass of the hydrate initially and then measure the mass of the anhydrate. So here, like I told you earlier, the difference will be the mass of water, right? So the mass of water, it will be mass of hydrate, and the subject is the mass of anhydrate. So this case, we can use mass of water divided by formula weight of water. So this case, likewise, mole of anhydrate, which is here, you can also use the mass of anhydrate divided by the formula weight of anhydrate. So the total Z can be found from this ratio of the moles, right? So here are examples. You can see this one is a typical, you can see for the, you can see that the copper sulfate with water. From here, I will not tell you how many water anymore. So write as that, Z. And this one will be something like this one's a cobalt. So cobalt 3. So that's the different powders. You can see the color and also associate different amount of water. And they will show that once you heat them, they will show different color, change that. So if you see that we heating will remove the water, right? And you see here, anhydrate is soluble in water. How do we know? Then you can simply put some of these anhydrates, put in the water, say they dissolve or not. That's how we know that, right? And here color change can occur from removing or adding water. This is exactly like I told you. For example, this one show here. This one has the water. Once we heat them, we'll go to this, will form the white color. No water here associated anymore, but this go back, we show color. So that's either way you can see the color change, right? And the process can be reversible, just like I showed that for the copper sulfate, you can do the possible reversible, either heating or add water. Some compound will absorb water from or lose water to atmosphere, we showed earlier, like the sodium, right? Like this case, or do that here. So our experiment, you will put it, so this one, make sure before you do anything, make sure this one's dry, right? Make sure this one's dry. So you will weigh a certain amount to that. Don't weigh less. Say you will try to use say less than 0.5 gram of your hydrate. Then in this case, the amount of water probably too small. So even you lose some water. The amount may not be accurately measured since we use top loading balance. So we will ask you to add the amount roughly about 1 gram, this amount added to that. And this net, you will cover something like this, never fully cover that, okay? So that's how we ask you roughly about 1 gram. So you need to record or observe the appearance. The appearance will include either color here or shape. This shape you can see that's one is crystal or not. And if that's a crystal, you can see this one crystal can be a needle or flare or flake, some different, you can describe that. And so these are the we will call appearance. Can be you can record the color and record the shape and the size. Roughly you can see somehow we will call powder. Right? Some is crystal powder normally not a crystal. And then you record the mass of this one plus this amount you add. So you can do either weigh this first, then add this one weigh again. And using sand, ring, and clay triangles and heat over Bunsen burners. So we will have a stand, something like this, right? And so you put a O-ring here. And so you put this one on top of that, and the bottom is Bunsen burner. Make sure the Bunsen burner are close to that one. It's about 1 centimeter distance. So that's how you can easily. So our Bunsen burner normally has a small blue flame. So here, do not completely close up with net. So this one allow water. So you see, I show you everything we do, we will have a purpose. So this one allow water to escape, right? And the heat till readiness about 10 minutes. So the readiness is here, set readiness, you probably not see that because anhydrous will be white. Sometimes you see the readiness means something further. So we will ask you just go to white. That will be okay. Then you turn the Bunsen burner off and cool for 10 minutes. Then you get the weight. And then you heat it again and cool and record the mass. If the mass of both are very close, then your experiment is finished. Now, sometimes if you have enough time, we will ask you to repeat this one, but for this class, probably just do one times. Otherwise, we will ask a student to do, actually for the analytical lab, we normally ask a student to do minimum 3 repeated measurement. But for this one, you just do one time. So if you see the mass are within 0.05 gram difference, then you're okay. Then you record the observation. Now, if not, if the difference is more than this one, then you need to add heat again for 5 minutes, then cool and repeat them. So reversibility check is this case, you can put it in a weight tray. So we have a plastic like tray, something. You put some of the powder, you after the hydrate put in, and you add 1 drop of water here. See what color change. So see what the water adds 1 drop water. See color change and the shape change. So this one, we will see them see that's reversible or not. Then you will clean the crucibles according to that directions. So we normally provide you several crucible because we want to, every time you use the dry to do the different experiment. In this way, you will finish for this one. So then you will continue to do another one. So repeat, we ask you repeat for those cobalt chloride and calcium sulfate for those two. So after the experimental, after your experiment, you need to record something like this one, mass of the empty and initial mass, right? And of the mass of a hydrate after first heating and the second heating, if these are close less than 0.05, you are okay. Otherwise, you need repeat and always record. These are the initial and so after the first one, and so for this time, you will always record the last one you heated. Say if you repeat this for 5 times, you normally record the last one and the first one, see they are very close or not. So if this one, say you have one, say this one, so 28.95, and the second one 28.75. You see the difference, right? Then you record 28.65 and 28.63. So now here you see this difference and less than that. So you need to record them to show that. But you need to describe how many times you repeated that. And so others you can describe somewhere. But here you can make another row to record all those numbers. So mass of a hydrate. So after addition, so this one second one additional you will put here. So next this one put here. Your observation, like I said, you need to record the color change as well as the shape change, right? And this one simply apply to those two columns. So after the experiment, you would finish the table, you will find the value for all the associated water with the three salt.